Good day everyone. Today we are going to see about the programming techniques in Turing Machine along with the halting problem and partial solvability. So we'll be using the programming technique in order to represent the Turing Machine as equivalent to the conventional computer. So we are going to use different techniques that are used to design a Turing machine. So there are storage in a finite control, multiple tracks. We'll be using subroutines and we will be using Chekhov symbol. So here we'll be using a Turing machine with a single tape or multiple tapes or with multiple heads. So let us first see the storage in finite control. So in this Turing machine, the finite control of the finite automata will be containing finite automata and the state transitions. That is, in this type of Turing machine, the final control will be having two components. One component is to store the state and another component is used to store the symbols. So here you will be using to hold a finite amount of data, and which will be shown in the diagram. You can see here in this finite control, Q is the state and A, B, C are the storage symbol. It can store three symbols with this, and it will be referring to the current type. So only one symbol will be referred in the input type. So this type of Turing machine makes the state to remember to have a memory for a scanned symbol in the input. So the state is Q and contains the symbols A, B, C for the current state A. So here this Turing machine can be designed to store the state with any data from the input. So it can store along with the data. Okay, so each and every state will be stored along with the data from the input, and each state contains a blank symbol as it is initially stored. Okay, so the initial configuration of the Turing machine, the finite control will be stored with the blank symbol. The Turing machine is used to store any symbol in the input and to check whether the stored symbol appears in the input. So it will be checking with the symbols A, B, C whether it is available in the input type or not. So what is actually storage in finite control? Each and every state will have a symbol associated with it. So we'll see an example how a storage in finite control automata will be done. So let us design a Turing machine that accepts the symbol 0 1 star plus 1 0 star. So that means so you will be having a language that starts with 0 followed by 1, or it will start with 1 that is followed by 0. So it either starts with 0 or it will start with 1 followed by 0 followed by multiples of 1s or 0. So if it is 0 means should be followed by 1s. If it is 1 means it should be followed by 0. Now you have to design a Turing machine using storage in finite control. So what is storage in finite control is each state will have a symbol associated with it. So you'll be using B for blank symbol. So initially the Q0 will be your initial state and B will be the blank symbol. So each state will have a symbol along with it for its understanding. So you'll just compare this symbol with the input symbol and you will make the transition. So what you are going to do here is, so initially when Q0 finds 0 or 1, it stores in the state without replacing and moves to the right and enters into Q1 state. So what it does is, so when it encounters the first 0 or 1, it will store it in its finite state or finite control, and then it will move to Q1 state and goes on. So in Q1, if it is, so we have two possibilities, either it can be 0 or it can be 1. So if it is 0, if it is 0 means in the finite state, then it should skip all the 1s and move towards the right and remain in the same state. If it is 1 in the finite control and finds 0, then it skips all the zeros and moves towards the right direction to find the blank space. So when these two states find the blank states, then it will become an accepting state. So let us draw a transition diagram for this. So as I said before, each and every state will have a symbol along with it. So Let us start with the initial state q naught comma b. So here I am using q naught comma b as my initial blank symbol, right? So initially you have two possibilities. If it is starting with 0 triple 1 means I have to do this. So if it is 0 for the input, it will go to q1 state. Okay, so you'll have q1 of 0. So let me draw it neatly. Q1 comma 0. So what will be the transition? If it is 0 comma 0, we will move to the right direction. Right. After scanning zeros, if you are encountering with 1, it should remain in the same state and it should skip all the ones. That means there is no updation. So you have to write 1 of 1 and move towards the right direction. Now, after reading all the ones, when it encounters the blank symbol, then if it is blank of blank, no update, we'll go to right. Then we'll enter into the final state. We'll take it as q1 comma blank symbol. So you let us be q1 of blank symbol. So this will be considered as our final state. So now this Turing machine has accepted the strings that starts with 0 and followed by 1s. Suppose it may start with 1 followed by zeros. So what will happen? So you will have to draw the same fashion. So we don't want another state. So here Q1 will record, will have input as 1. So you can see the number of states will be very less. So if it is 1 of 1, it will move to the right direction. So if 1 is followed by multiple zeros, then it will be 0 of 0 comma right direction. Then finally it will move to the final state when you encounter a blank symbol. So now let us see the definition of Turing machine. So the Turing machine definition, M. So M is equal to, so you have to draw, you have to write the states along with the blank symbol. So it is first Q0 with the blank symbol. You can see it is Q0 with blank, Q1 with 0, Q1 with 1 and Q1 with blank. So you will have Q1, then Q1 with 0, Q1 with 1, then Q1 with blank. So these are the states. Then next, the symbols that are used, the set of symbols or terminal symbols. Here 0 and 1 is the terminal symbol. And what are the tape symbols we have used? 0, 1 and B is the tape symbol. Then we have a transition function. And what is the initial state? Q0 comma B is my initial state. And what is the final state? So the final state will be, so here the blank symbol we have used is B. And what is the final state we have used? We have used Q1 comma B is my final state. So this is the Turing machine. Now the transition function is, so this is the transition function for the given Turing machine. Okay. So you can write it like this, or you can put it in a table. So if you write it as a thing, you'll write it like this. If it is Q0 of B with the input 0, it goes to Q1 comma 0 with no updation and to the right direction. So you can write the transition function like this, or you can use a transition table. So next, the programming technique is we are going to use multiple tracks. Okay, so multiple tracks in the Turing machine. So what is the multiple tracks in the Turing machine is? In FSM, you will be using two components. That is, in storage in finite control automata, you will be using two components. One is state and another one is memory, and memory is used to store the symbols. Now we are going to extend the Turing machine that is going to include multiple tracks in the input tape. Okay. So in this Turing machine, the finite control contains state and storage, but the input tapes will be of multiple tracks. So each track in the input tape contains only one symbol. That is, each track, one cell will be having only one symbol. The tape alphabets of the Turing machine will contain one component in each track, and the number of components in the tuple depends upon the number of tracks on the input tape. For example, when the finite control reads, it will be reading all the tracks at the same time. So in finite automata, you have a single tape, then it will be reading only X. For example, so if this is the control and you have a tape means and you have A, then here you will be having only one symbol over here for finite automata. But in your using multiple tracks, so the Q will be having three symbols. For currently you can see the control is reading X, Y, Z, then you will be having X, Y, Z. So this is the difference between the single track and multiple track symbols. So the multiple track will be used to find whether a number is odd or even, or it will check whether the number is prime or not. So this is how the multiple track is used. So let us see an example how the Turing machine is used with the multiple tracks for solving the problem. So now we are going to design a Turing machine using multiple tracks to check whether the given input is palindrome or not. Okay, so we are going to use multiple tracks to find whether an input is palindrome or not. So we know that how a palindrome will be checked. So here we'll be having three tracks. So what we'll do is the track 1, I will take it as 1 will be containing the input, and track 2 and track 3 will be blank. So it will be filled up with the blank symbol. For example, let us take, I'm going to take a symbol A, B, B, A. So what is the procedure we are going to do? We have already seen it in a Turing machine example. So when you scan the first A, we will travel towards the rightmost to the blank symbol. When it sees blank symbol, we'll change its direction to the left. After encountering a blank symbol, we will change towards the direction of the Turing machine, and we will see whether the next symbol encountered is A or not. So how it works is, so we'll see an example. So first thing is, if you have, I will take a symbol. Okay, we'll have it here itself. For example, you will take ABA. So initially we'll start with the Q0. We'll read this. We'll change it in move in the right direction. We'll change it into some symbol. So what I will do is I will change it into dollar. Okay, so you'll be changing into dollar. So what happens is it will become dollar B A. Then we will move towards until the blank symbol. So we'll move, once it is encountered with the blank symbol, we'll change it to its left direction, and you have to see an A itself. So it will become dollar. Then again it will travel towards the left direction to see a dollar. Then it will change its right direction. After changing, then you will encounter B. Then this B will have a separate path. So you will be having one path that starts with A and one path that starts with B. So this is how we are going to design a Turing machine. So let us see how it is done with multiple tracks. Okay. So let us have a three tracks. So I am going to draw like this. So this is. So let me have A, B, B, A. So this is track 1, this is track 2, and this is track 3. So initially all this filled up with the blank symbol. So here what you are going to do is we will consider all three symbols for our possibility case. Okay, so we will be considering all the three symbols for my possibility. So let me draw with one color for first symbol. So let us consider only A alone. Okay, then we'll check with anything. So initially we'll start. So I will draw with Q0. Okay, so I will be going to Q1 when it is A B B. So it is going to be A B. Okay, sorry, it's a blank symbol, so you will write it as A B B. You will update this first A with some symbol. So let me use a symbol called dollar. So now it is dollar. So you will write it as A dollar blank, and I will move towards the right direction. So now you will be in Q1. Now what I have to do, I have to travel towards the towards the rightmost A. You will be traveling towards the rightmost A. So when you travel, you will encounter B and A. So if you have multiple A's or multiple B's, then you will just change it. So I will have a self transition over here itself. It is A B B, A B B. I will travel towards right. Or if it is multiple B's, I will travel towards right. So what happens? My control travels from B to here, no change, Q1. Then finally A, it will jumps. Then finally it will encounters a blank symbol. So when it sees a blank symbol, we have to change its direction. So what I will do here is, so if it is triple blank, then I will change my direction to left. So this will be my Q2. So now it has changed the direction. Now you are in the left direction, and if you are encountering A, B, B, so you will be A, B, B, change it to A dollar B in left direction. So you will travel towards the left direction. Now I will be going to the next state for Q3. Now what happens is this A will become dollar. So here A will not be changed anything, only the blank symbols are going to be changed. So we will not change the input. So you can see it's done. Now you have to travel until this dollar symbol. Okay, so now you have to travel until this dollar symbol. So you can encounter multiple A's and multiple B's. So I will have A B B or A B B. I will travel towards left. B B B or B B B, I will travel towards the left. So when you encounter A dollar B or B dollar A, okay, so it can be either A or it can be either B. So I have to do, so if it is A dollar blank symbol or B dollar blank symbol, then I must change its direction. So no, with no updation, I will change my direction. So now it is B dollar B. I can change my direction. So what happens when it sees the first dollar? It will change its direction now to the right side. Now you have seen B. So now let us see what are the other updations you can travel. Now if you have multiple A's, when Q2 is traveling, you will be traveling with a when Q1, when you made a multiple A's, you may have encountered multiple dollar symbols or anything like that. So you can take it as here A dollar B and A dollar B. You can travel left. Similarly, you can have B dollar B also and B dollar B also. So you can travel left. So now this is done. This is for string starting with A. Now you can see my string is going to start with B. So let me have another color over here. So I will take this as Q4. Now you can see we have changed $2. Now this is dollar and this is dollar. You have a blank symbol, you have blank symbol and blank symbol. Now we are in this B, so it has to be changed into dollar. So now this should be changed into dollar. So what you will do is you will have, if it is B of B dollar B, then you do travel right. So this will be of similar to this same path. So let me finish it off. So this B is done, which is similar to the similar path, just vice versa you'll do for B alone. Now what happens after this B is made as a dollar, then it move towards until a dollar B or B dollar B or until a blank symbol. So you can encounter with a dollar. So when it turns, it changes its direction towards left. When it changes, when it encounters B triple B, this will be updated as a dollar symbol. So now it is made as dollar symbol. It goes to Q6. Now Q6, if it is, it has to travel. So if it is a dollar B, it will change its direction. Now it will change its direction. Now you can see if it is changing its direction, now you will not have any possible cases with the Q1. Okay, so what it has to do is it has to, when it encounters a dollar B, and it has to travel a dollar B until, or then if it is B dollar B and B dollar B, it just travels to the right. Now what is happening is Q0 will travel from here to Q7. So you will just travel until you encounter a blank symbol. So you will be traveling it. So you will have again a dollar B or a dollar B towards right, and B dollar B and B dollar B towards right. So when it encounters B B B or B B B towards right, it will enter into the accepting state Q8. So we will check that the second half does not contains any other symbol to its end. So this is the Turing machine we have designed. So this Turing machine, you will be writing it as m is equal to, so we know that you have Q0, Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8. So here I have written only few of the transitions, so rest of the transition I didn't write it, so you can complete it by yourself. So into A and B. So the terminal symbols you have used is A and B, and the tape symbols we have used here is A, B and B. So we have a transition function, and you have a blank symbol as B, and your initial state is Q0 and your final state is Q8. So the transition functions are given as the table. The remaining transition functions you have to write it by yourself. Right. Next symbol is we are going to use a programming technique, that is checking off. So what is checking off symbol is, so you are going to extend the Turing machine to a next level using checking off symbol. So here we are going to use this checking off symbol to check the language that has a repeated string, or to compare the length of two substrings. For example, we are going to use the checking off symbol with a language like WCW. So that is W is repeated after C or without C. Okay, or it may be a reverse. So W by WR, which is nothing but a palindrome. It is a palindrome symbol. Okay, so it is meant for palindrome. So we'll check, we'll take the first example and we'll see how a Turing machine can be designed using a checking off symbol. So what is checking off symbol is, here we'll be using symbols star to refer that this symbol or this state is already been processed. Okay, so let us see an example. So design a Turing machine to recognize the language L is equal to WCW, where W is equal to A comma B star. So the here idea is to design a Turing machine that recognize the language to using a checking off symbol. So here we will be representing the initial state like storage of finite control. So each state will be having a symbol with it, and the second component will be a symbol of it. So for example, it will be like Q0 B. So you will be using a storage finite control format. So here, when you are initially in 0, we will start moving towards the right until we see a C. When you see a C, we'll check whether again 0 is present after C or not. So here it is going to be A. So we read A initially, then we move right towards until we read C. After reading C, we will check whether A is present or not after C. Similarly, when you read B before C, then we move right towards the C to check whether B is present or not. So simple. You'll be having like ABC, ABC. So what happens when you will start make this as X, we'll move towards C. After C is done, you will check whether A is there, then you will make. Then you will change your direction, we will move towards C. We will see whether the first B which is going to be there, we will change it as Y. Then we again travel towards the end and we will change it as Y. So after this, we will have to move. So here, we are going to use a checking of symbols, so we have to use the symbol in a different format. That is the tape symbols, or the symbols will be used. For the example, the terminal symbol 0, 1, C will be used as B, 0, B, 1, B, C. Why, sir? So initially when they are not processed, they will be of B, 0. When they are checked or when they are processed, it will change into star 0. It will be changed into star 0. So this is the example for this one. So let me draw the transition diagram for this, so you will be able to understand. So I will draw it up first one. So we will start with the initial state. It is Q0, B. So I will be going to so we'll take it as, why do we have to always start with Q0? I will start with Q1. So I'll be going to Q2 with the input 0. So because when you encounter 0 or A, okay, so we'll take it as, here I would given it as AB. So let me finish the diagram first and we'll see an example. So we have seen an example. Now we'll start with the initial state Q1 here. So when it sees 0, okay, so we'll, as I said before, 0 will be referred as B, 0. You can see it is B, 0. I will mark it as asterisk. I will mark it as it has been processed. Then I will move towards the rightmost blank symbol. So you can see it can encounter either 0 or it can encounter 1. So it will continue its right direction until it sees C. It will go to the next state, that will become Q3. When Q3 comes, it will have a self transition until it is a star 0 or star 1. So we'll see an example for when it comes for 1. Now Q3, when it encounters 0, this should be made as star and it should change its direction towards left. Now what happens is 0 has become star 0. So now this is the star 0 over here. Okay. So once it is done, again it travels, it may encounter star 0 or star 1. So from when it sees Q, then the next symbol very next to C in left side has to be processed. So when it sees C, it goes to a new state called Q5. And when it sees 0 or 1, it will travel towards the left direction until it encounters a star, because it will see the star is here. So now what happens is, now the control will move from C to 1. Then when it sees 0, it will change its 0 and star, that is the star 0 symbol is being processed. It will change its direction to the right side. So you can see star 0, then there is no updation, it will be star 0 and it will be changing its direction to right. So now what you will be having here is, like this. So it is 0, 1, C, 0, 1, C. Now it will become star C, 0, 1. So until this, it will move towards this. So after this, it will become star 1, C, star 1. Now it will change its direction. It will go here. So it will come to X. Now when it's come to Q1, now you can see it is starting with 1. So you will have a separate diagram for transition for 1. So let me finish that. So now what happens is, it will make 1 as star. It goes up to C. Then after C, you can see you have a star. So you have a transition over here. Q3 will be making a transition. Then it goes up to star 1. So when it is made 1, so now it will become star star C, star star C, and change its direction towards left. So until this star it works. So until this star is works, so what happens, it will come to Q5 BCC. Then you will not have a transition after this Q5 over here. So I have to give a transition over here. So I'll change my state. It is Q7, B. So after all the C's have been done, we'll move towards the blank stage. So what happens after C? You will enter a Q5. Then now Q5, you can see everything is start. So all the symbols are start before the C. So you will enter into a new state called Q7. You will change your direction. So you will change the direction to right side. Okay, we move towards the blank symbol. So what happens is star star C, star star C, blank symbol. When blank symbol is encountered, you can see when blank symbol is encountered, we'll enter into the final state. So now this is for even number and odd number. If suppose you have only C alone, then that is also to be accepted. So what we do here is we'll have a separate state for that. So you'll have it as Q2 with C alone. Okay, so we'll have a Q2 with C alone. Suppose if you are encountering only C, then you'll mark the C and move towards the right. And if you have only the blank space after C, that is the only string is given as C alone. Okay, so you don't have any other word before and after C, so then that should be also accepted. So you'll be having B comma B. If it is a blank space after C, no change in the blank space symbol, we will enter into the final accepting state, right? So we'll go for the Turing machine definition. So you know what are the states we have. Okay, so here we will write it like this. So your Turing machine M is equal to Q comma sigma comma tape symbol comma tau Q naught B and F. So we know that Q is going to be with the state Q0 to Q9 into the symbols 1 and B. So you can, instead of writing it in this complete form, you can write like this, and summation is going to be 0, 1 and C, which is written as B comma 0, B comma 1 and B comma C. So similarly you will have a tape symbol, so you will be having B comma star. Okay, so this will be crossed with 0 comma 1 comma C comma. So this is the tape symbol we have, right? So the next the transition function, you know what is the initial state. So initial state is Q1 comma B is your initial state, and Q9 comma B is your final state, accepting state, and the blank symbol we have used is B comma B. So it's not a curly brace, it's a square bracket. B comma B is a blank symbol. So the transition function is, so this will be your transition function for the given diagram. Right, next we will go for the subroutines. So in some problem, we need to perform a same process repeatedly again and again to solve the problem. For example, that type of problem is called as the subroutines, or we'll call it as a function. Let us see how subroutine is used in a Turing machine. So the subroutines will be having one start state and another state which namely called it as a return state. So in a subroutine function of the Turing machine, there will be a one state called start state and there will be another state which will be called as a return state. So what return state does is it does not move the tape head. Instead of that, it will transfer the control to the Turing machine which has called the subroutine. Okay, so whenever a subroutine is called, the transition will be made to the initial state of the subroutine. Whenever the subroutine call is completed or it will be moving, so it will be passing over the control to the called Turing machine. So each calls made for a different subroutine will handle a different copies of input. So the same copies. For example, if one subroutine 1 is calling subroutine 2 for the same function itself with different input, means it will have a different copies for each call. So this will be performed, all the subroutines will be performed simultaneously. So let us see an example how subroutines can be used. We will take a simple example how to perform multiplication of the numbers. So the idea here is we'll be using a representation 0m, 1n and 0n. So m and n is represented as om and on. So you will be using one to differentiate the argument and another one is used to represent the end of the second argument. So one is here is used to represent the end of the each argument. So how it will be represented in the tape, you can see in the input tape. So when m is equal to 2 and m is equal to 3, you will have 0 0 for the first part and 3 zeros for the second part. That is o of power m and o power n, and each argument is separated with 1 over here. So finally, after performing the multiplication, how the output will be. So it is 2 into 3, it is going to be 6. So you'll have 6 zeros in your tape. So you can see 1, 2, 3, 4, 5, 6. So you have 6 tapes in the tape. Now let us see how to perform the multiplication. So the initial step, what you will do is, when a 0 is found in the input, we will try to replace it with a blank symbol and we will move towards the searching of 1. So for example, if you have 0 0 1 0 0 1, so it is 2 and this is 2. So first I will make this symbol as blank. For this 0, these two zeros has to be repeated. So what after is, after finding 1, call the subroutine and copy n numbers of 0 for m times. So this is n number of zeros that will be repeated for m times. So what is m times? For the first time. So what happens is, after this one you will have 2 zeros. Okay. So after performing, you will travel towards again here. We will make again this one is b. We will go here again. How many zeros are here? N times. So you will have 0 0 0 0 over here after this one. Again, when you travel, when it is blank, we will change all the symbols into a blank symbol. So initially what will happen here is, you will be having it as BB 1 0 0, this one. So now the tape will start moving towards the blank symbol. So when it sees first one, it will make it as blank, second one it will make it as blank, and third one it will make it as blank, and one it will make it as blank. Then after this one, if you have any zeros, it will not be changing, and then finally your answer is obtained. You will have blank blank alone. So this is how multiplication is performed using a subroutine. So you'll see how subroutine is used over here. So the simple idea is, for each 0 in m, the n zeros will be repeated for performing the multiplication. So let us see how a transition function we can design. Okay, for the first thing, so we will write the transition function for the subroutine alone. For each one, the 0 0 1 0 0 1. Okay, so when this is made b, for this single b, this has to be repeated twice. Again, this has to be repeated twice. So we'll have two transition diagrams. Okay, we'll draw it in a different fashion. I will draw it. So we will see an example. So when it sees 0, it will change it into blank. So I have changed it into blank. Now I will enter into, so forget about the numbers of the queue state. So I will traveling towards the first one. So it will travel towards the 1. So it discards the number of zeros. So 0 0 will be discarded. So when it sees 1, it changes its states into Q1. Now this should be added for this many number of times. So how many zeros we have for m, that many times n should be read. So I am calling a subroutine function here. So this is how it will be considered, Q1 and Q5. So I have some functions over here. Now what happens in Q1 and Q5? So let us see the subroutine function here. So in the Q1, when you encounter 0, okay, I will change it into x. So what happens? This will become x. So you will have, I will write it like this. So you will have b01 x 01 0 0. For this many, okay, it's not 0 0, it's just x. So after seeing x, we will go to Q2. Okay, so now you will discard all zeros and ones over here. So let me have a self transition. So if it is 0 0, I will move right, or if it is 1 1, I will move right. So it comes to after 1. So when it is comes to a blank symbol, so when it sees a blank symbol, I have to change it as 0. So what happens is, it moves on towards the right. Finally, it will make it like this: 1 0 x 0 1 0. After making this, it will change its direction towards left. So what I do here is, if it is a blank symbol, I will change it as 0 and I'll change my direction as left. So now this will be off in Q3. Now Q3 travels until X. So it has to travel until X. So you will have either 0 or 1. So 1 it is left direction, 0 or 0 it is left direction, it moves towards this. So once it sees X, it will change its direction to right. So what happens before X, it will be standing over here. Now B001 X it will be converted because it's in Q1, again it will be changed and you have 00B. Now what happens, it travels again towards the blank symbol and it will make it as 0. So you'll have B01XX 1 0 0, then you will have following with the blank symbols. Now it travels again towards X. Now X is there. When it encounters 1, it is the end of the end term. So you should travel towards. So after X, it will travel towards this. Then after this, it will change its direction towards the left itself. So now 1 is here. It will change its direction left. What happens? This will become 0. What happens is, it will change all the X into 0. So 0, X1, 0, 0. Then you will have B01, 0, 0, 1, 0, 0. So how do we do it? When Q1 is there, there is no more 0. You are encountering with 1. I will change my direction towards left. I will be entering into Q4 and I will update all the X's into 0. So it will be X0 into right. Sorry, not left. It is not left, right? It is left. So I'll update it. Then when I encounter 1, it is end of the first n term. So I will change it into right direction and I'll go to Q5. So what happens after this? You will encounter, when it encounter 1, so you will stop here, you will be having Q5 here. So now this is the subroutine call. Now when you come out of Q5, you can see 0, 0 to the left. Okay, then you will come to you will change your direction. So you will be in here Q5. If it is 0, you will change your direction to left. If it is 1 also, you will change it to Q8. If it is 0, you will travel towards the blank. When you see the blank, again you will come to Q0. Again the same process will be repeated. So now what will be the process will be repeated is, the second 0 will become B. So I will write it over here. Second B will become B and you will have 1, 0, 0, 1, 0, 0. Now the subroutine function will be called and this will become X 0, 1, 0, 0, 0. Then again X, X 1, 0, 0, 0, 0. Then when you travel back, okay, so this will become zeros. So you'll have B1X, BB1X. Then it will be getting into BB 1, 0, 0, 1, 4 zeros. Now when you encounter blank space, so you are entering into your final state over here. So when you encounter a blank space, now when you be entering into your blank space, so it is blank of blank towards right, you'll change your direction to right, you'll enter into Q10, okay, and all the ones will be made blank. You'll enter into Q11, all the zeros will be made blank, so and still move. So what happens is, this will become blank, all the zeros will become blank, then final 1 will become blank, so that 1 will become blank, and finally you will enter into Q12. So that's your final state. So this is how a subroutine function is called using for performing the multiplication. So let us so I have given a transition table for separately for the main diagram as well as for the subroutine. So this is for subroutine and this is for main function or calling function of the Turing machine. Okay, so that's all for the sum. The next thing is we will be seeing about a halting problem. So what is a halting problem is the intractable or undecidable problems are called as the halting problem. So in a Turing machine, if the input of the Turing machine does some finishing computing, so in the Turing machine it has to finish all the process in a finite amount of time or finite number of steps. So in order to solve a problem, you have to get the answer either yes or no in a finite amount of time. And the machine has to give regardless of the input format. So if you may have multiple inputs, because of without the consideration of the input, the Turing machine has to give either yes or no for the problem. So there are some problems we are not able to find the answer, and such problem halts in a unrepeated state, that is in a rejection state. We say that problem is a halting problem, and the Turing machine which recognize that kind of problem is called halting machine. So what is an halting machine? An halting machine is a machine that operates on another machine and its input produces either yes or no answer in a finite time. Either the machine is in question finishes in finite time or it does not. Okay, so the process may finish in finite time or may not. It may enter into infinite loop. It may has to give either yes or no in a finite number of steps. Then that kind of problem is called as a halting problem. Now what is partially solvability is, if a problem P is partially solvable if there is a Turing machine T that partially solves the problem. Okay, so that is, it solves for a particular instance of the P, it will be correct, and for the particular instance of P, it will be wrong or it will be getting rejected. A problem with a set of yes and no's. Okay, so we call it as a, we will divide it into three parts. For example, you will tell it as it's a base set, and you will have a set of answers, that is right answers, that is going to be yes or no for each object. For example, if it is going to be a blank tape halting problem, you will be having a set of Turing machines. So you will be having some set of Turing machines, and for a particular instant, you will assign a particular Turing machine, and that Turing machine will be having yes for some part of the blank tape, and it will have no for some part of the blank tapes. So this problem is partially solvable if there is a Turing machine is given encoding on T and halts and say it is accepted, because if their entire tape is filled with blank only. For particular sequence of reading itself, it will say it is getting into a halt position and it says it is accepted because it consists of blank symbols. Sometimes it may not have a particular stage, it will enter into an infinite loop and it goes on and it enters into a failing answer and says it is not, it fails on halting the tape. So you will get the same answer for same instance. That is the problem of partial solvability. So what will be the properties for the partial solvability is, if P is decidable, so I decide that my answer is correct or my answer is rejected, then we say that the problem is partially solvable. If both the P and the complement of P are partially solvable, then we may say the problem is a decidable one. Okay, so you will be having an encoding. So you will have a set of instance for accepting state and a set of instance for rejection state. So this is how a partial solvability problem is used in the Turing machine. So thank you. So that's all for today's class. We'll meet in a new topic in the next session. Thank you.